Good evening to all. Myself S.Ramesh, Department of Statistics, anrcollege, Gudivada. Today we are going to discuss about assignment problem. Content in assignment problem. Introduction to assignment problem. Matrix form of assignment problem. Mathematical formulation of assignment problem, algorithm for assignment problem or Hungarian method, example of assignment problem. Introduction to assignment problem. An assignment problem is a particular case of transportation problem. In many business situations, management needs to assign persons to jobs, jobs to missions, missions to job locations, etc. Consider the situation of assigning n jobs to n missions or persons. When a job I is assigned to mission J at a cost Cij. Suppose that we have n jobs to be performed on m missions. One job is to be assigned only one mission. Under mission, the assumption that each mission can perform each job but with varying degree of efficiencies. Our objective is to assign the jobs to the missions at the minimum cost or maximum profit. Matrix form of assignment problem. The assignment problem can be stated that in the form of m by n matrix, Cij is called a cost matrix or efficiencies matrix, where Cij is the cost of assigning ith mission to jth job. Mathematical formulation of assignment problem. Mathematical formulation of an assignment problem. Consider an assignment problem of assigning n jobs to n missions, one job to one mission. Let Cij be the unit cost of assigning ith mission to the jth job or jth job to ith mission. Let Xij equal to 1 if jth job is assigned to the ith mission. Xij equal to 0 if jth job is not assigned to ith mission. The assignment problem can be expressed as a linear programming problem. Minimum Z equal to double summation, I running from 1 to n and j running from 1 to n, Cij, Xij, subject to the constraints summation I running from 1 to n Xij equal to 1 for j equal to 1, 2, and so on n, and summation j running from 1 to n Xij equal to 1 for I equal to 1, 2, and so on n Xij equal to 0 or 1. Algorithm for Hungarian method or assignment problem. First, to check whether the number of rows is equal to the number of columns. If it is so, the assignment problem is said to be balanced. Then proceed to step 1. If it is not balanced, then it should be balanced before applying the algorithm. Step 1. Subtract the smallest cost of each row from all the elements in that row of the given cost matrix. See that each row contains at least one zero. Similarly, for columns, subtract the smallest cost element of each column from all the elements in that column of the resulting cost matrix obtained by step 1, and make sure each column contains at least one zero. And third one, assigning the zeros. For assigning the zeros from the earlier UPF matrix, we have to examine the rows successively until a single zero is found. Make an assignment to this single zero by square box or circle, whatever it. Cross all other zeros in that column, and it will not be considered for any future assignment. Continue in this way until all the rows have been examined. Similarly, for columns, examine the columns successively until a single zero is found. Make an assignment to this single zero by circle or square, and cross all other zeros in that row, and it will not be considered for any future assignment. Continue in this way until all the columns have been examined. And step 4, here we have to apply the optimality test to find the optimum solution. In this case, if each row and each column contain exactly one zero, circle 0 or encircled 0, then the current assignment is optimal. That is, if the number of persons is assigned to the number of jobs, then we have to attain the current solution is an optimal solution. Otherwise, if at least one row or column is without an assignment, that is, if there is at least one row or column is without one encircled 0, then the current assignment is not optimal. Then go to step 5. Here, subtract the smallest cost element of each column from all the elements in that column of the resulting cost matrix obtained by step 1, and make sure each column contains at least one zero. Now, here we have to draw the minimum number of horizontal and vertical lines when the number of persons is not equal to the number of jobs or machines. In that, first of all, mark the rows that do not have any assignment, and mark the columns not already marked that have zeros in marked rows. And third one, mark the rows that is not already marked that have assignments in marked columns. Repeat step B and C until no more markings is required. Now draw the lines through all unmarked rows and marked columns. If the number of these lines is equal to the order of the matrix, then it is an optimal solution, otherwise not. Now, from the reduced matrix, determine the smallest cost element not covered by the straight lines. Subtract this smallest cost element from all the uncovered elements and add this to all those elements which are lying in the intersection of these straight lines, and do not change the remaining elements which lie on the straight lines, and repeat steps 1 to 6 until an optimum assignment is obtained. Now, if you take an example on assignment problem by applying the algorithm of Hungarian procedure to assign the number of jobs to number of persons or machines, solve the following assignment problem shown in the table using Hungarian method. The matrix entries are processing times of each job to each machine in hours. Here there are 5 persons and 5 machines, and it is the cost matrix for number of persons assigned to the number of jobs. So the payoff matrix of order is 5 by 5, so that it is a balanced assignment problem. If in any case the number of rows is not equal to number of columns, then you must equal to the number of columns and rows. Whenever it is not equal to the number of rows and columns, that case is known as the unbalanced problem. Here we have to not apply the Hungarian procedure for unbalanced problem. Hungarian procedure is applied only for balanced assignment problem. Now, here the given cost matrix is a square matrix. So we have to apply the Hungarian method to obtain the optimum solution. Here, from the given payoff matrix, we have to apply the row subtraction and column subtraction. Initially, we have to choose, or we have to make the row subtraction or column subtraction either row or column wise, whatever your interest. Now I am choosing the row wise subtraction. In this payoff matrix, select the smallest cost element of each row and subtract it from all the elements in that row of the given cost matrix. See that each row contains at least 1 0. Now, from the earlier payoff matrix or given cost matrix, in first row there is a smallest cost is 15. Now, this 15 is subtracted from all elements in this row only, not for all the rows. Similarly, in the second row, the smallest cost is 12. Now, subtract it to the smallest cost from all elements of this row or from this row. Similarly, remaining columns, now select the smallest element of each row and subtract it from the all elements in that row. Then we get the reduced matrix or payoff matrix. From the payoff matrix or earlier matrix, whatever we have to apply the row subtraction. For that matrix, we have to apply the column subtraction. From the reduced matrix, we choose the smallest cost element of each column and subtract it from all the elements in that column of the given cost matrix and see that each column contains at least a single zero. Now we make the assignments. For making the assignments, you have to observe you must observe all the rows and columns must be having a single zero. So in the earlier payoff matrix, here there are single zero. There is at least single zero in each row and each column. So we make the assignments by applying the row wise and column wise by Hungarian method. Now make the assignments here in the payoff matrix. We have to make the assignments having only a single zero or single row or column. In this payoff matrix, in first row there are 3 zeros. So leave the first row and go to second row. In this row there is a single zero and we have to assign this zero and cross out all other zeros in this column. And from the third row there is a single zero in third row, second column. We assign this zero and cross out all other zeros in this column. And fourth row have to single zero, so have to assign this zero and no other zeros have been crossed out. And from the last row there is no single zero, already a zero is crossed out. Similarly, we have to apply the column wise. Whenever we have to apply the horizontal, have to apply the assigning the zeros by using the conditions, there must be number of assignments must be equal to the number of persons or number of jobs equal to the number of machines. Here the payoff matrix is 5 by 5, that is there is a 5 persons is assigned to the 5 machines. So we are obtaining the here only 4 assignments. So we are not attained the optimal solution. So that for obtaining the optimal solution, we have to draw the minimum number of lines through cover all the zeros. Here to draw the minimum number of lines, we have follow the some conditions. One is the already earlier slide we have to seen. So we have to use the principles of drawing the lines. We have to draw the lines from reduced matrix to get this reduced matrix. Now making the assignments to obtain the equal number of assignments. Here there are we got the equal number of assignments in each row and each column. So we get the optimal solution. So we have to write the optimal solution from the given payoff matrix or cost matrix. In the earlier payoff matrix, the first job is assigned to the third person or third mission, and the second job is assigned to the first mission, and third person is assigned to the second mission, then fourth person assigned to the third mission, and fifth person assigned to the fifth mission. Here there is a single assignment in each row and each column, so we have to obtain the optimum solution, that is 11 plus 43 plus 28 plus 27 plus 25 equal to 134 hours. It means the number of jobs is performed on number of missions of the requirement processing time. Thank you.